relatively small amount comes from refineries. But on the other hand, because there's not much gas used in the chemical industry, mostly naphtha, we can get a lot of the propylene from the naphtha instead of the gas. So that's how Europe solves that situation. In the Middle East, it's still mostly light feeds, not a lot of need for refinery propylene. But in Southeast Asia, first of all, look how big the demand is for propylene in Asia Pacific. Most of it comes from steam crackers, but a fair amount comes from other refineries as well. Now, one point I haven't mentioned yet is this OPP, and this is very important, and it will be what I will be talking about in the remainder of my presentation. OPP stands for on-purpose propylene, and those are technologies such as propane dehydro and others, and these technologies are starting to fill in some of the supply gap around the world. As you can see in Asia Pacific, a couple percent of demand is already filled by on-purpose propylene. The same is true in the Middle East. If the Middle East wants to participate in the propylene markets, this is on-purpose propylene are technologies they would like to consider because their advantage in propane versus the rest of the world is not as great as their advantage is in ethane compared to the rest of the world because it's so difficult to transport ethane. And there's also some on-purpose propylene going on in Western Europe. Okay, I call this the case of the missing propylene supply. Where is propylene production heading and what will be its sources? To crack this case, first we must follow the ethylene. So instead of following the money, we must follow the ethylene. This is a chart of incremental ethylene demand from 2004 to 2012. Okay, so that means not total demand, just new demand from 2004 to 2012. Again, this is kind of interesting, but not very informative. It's really not even very interesting at this point, to tell you the truth. Now it's starting to get interesting, but still not informative. Now we overlay propylene demand next to ethylene demand, and we take a look at the ratio, and it's a fairly reasonable 0.61. Remember I said a naphtha cracker gives you about a 0.5. So naphtha crackers alone could not meet this demand. We're going to have to use other technologies or rely on our refineries for FCC propylene. But this is on a global basis, and this is not a global market just yet. It's still a regional market, so we need to look at what's happening in the individual regions. So now we have incremental ethylene demand on a regional basis from 2004 to 2012. And you can see now where the action is going to be, the Middle East and Asia Pacific for sure. Now we overlay propylene demand on a regional basis, and we get this graphic, and we see for propylene, Asia Pacific is where the action is going to be. And if we compare them side by side and look at the ratios, now we start getting both interesting and informative. In the US, we have a fairly high PE ratio expected into the future of 0.77, but overall demand is relatively low because of the US is no longer a low-cost ethylene producer because of the high cost of both gas and oil in the US now. South America, it's not going to be a problem. It's a very moderate 0.44, and overall demand is relatively low. In Western Europe, we get a very high ratio, 1.5. Western Europe is going to become very propylene-centric as far as new production goes, but the demand is relatively low. That's because Western Europe is also a high-cost producer, and of your proximity to the Middle East, where the Middle East is going to be importing a lot of things into Western Europe. The Middle East is still going to be fast-growing in ethylene, and that ratio we expect to remain about the same at 0.24. So ethylene, Middle East will still be mostly ethylene-centric by 2012 is our expectation. In Asia Pacific now, we see a very high growth for both ethylene and propylene, but propylene is now catching up. It's almost in a 1-to-1, 0.85 ratio. And we'll talk about this a little bit more. It'll be very important. This is not to say that ethylene derivatives are not going to be important in Asia, but the Middle East is going to be importing into China. So most of the in-country production in China is going to be propylene derivatives. Okay, let's take a look at each region on its own and see what we expect. As I said, overall demand is tempered by high-cost feeds. The region will continue to source incremental propylene from its refineries, and we don't foresee any supply problems. As far as on-purpose propylene, BASF, Untitled Cracker, the new cracker reported off from Texas, is using the Lummus technology. And the reason we think they would like or are using that technology, we wouldn't have necessarily predicted that, perhaps the Lummus people can tell us a little later today, is that BASF and Olefin are very propylene-centric. BASF has developed a very strong business based on a variety of propylene derivatives, and Olefin is very strong in polypropylene. And the refineries will continue to use these new FCC additives, which will continue to increase the propylene output from the FCC units. South America, the region continues to be ethylene-focused, although two of the cracker projects in the region are ethane-based. Propylene molecules, as I said, will be plentiful. We don't see a lot of opportunity for OPP in South America. Western Europe, although the PE ratio is very high, we see demand in the region is being tempered by high costs and proximity to the Middle East, but we see the availability of propylene molecules in refineries is reaching exhaustion. So we do think there will be opportunities for OPP in Western Europe, but we think these will be for niche products, for high-value products such as propylene oxide and acrylic acid. And we also see propylene refining. Boosting technologies will also continue to find use. Middle East, as I said, very fast growing, but ethylene will still remain supreme. Continued use of ethane as a key feedstock should provide opportunities for on-purpose propylene. If the propylene derivative platform is to grow, there are propane dehydro projects in the Middle East. An interesting concept is to dimerize ethylene to butene, followed by metathesis with more ethylene to give propylene. So this would be a way to make to make propylene only from ethylene using a very low-cost ethane. So I think this is a good and interesting idea. Asia Pacific, as I said, the region is very fast-growing due to high local demand. This high PE ratio is continuing to increase, and coupled with high demand, will put stress on conventional propylene sources. So we do see a lot of opportunity for on-purpose propylene in Asia. Metathesis is gaining favor in this region. My buddy Steve Kantorowicz in Lummus has done an excellent job selling this technology. Every place I visited to try to sell consulting services, it was little Stevie was already there and doing a good job apparently. Propylene boosting technologies in refineries will also continue to grow. So that's our view, that's Nexen Chem Systems' view of the future, at least out to 2012, with regard to propylene technology, with regard to propylene demand and supply. For the next, say, 15 minutes, we'll look at some of these on-purpose propylene technologies. I don't want to say too much about them because I think for each and every one of these technologies, we have the actual technology providers going to be talking more in depth. So I'll try to just give an overview. Okay, on-purpose propylene technologies, the industry brainstorms. Of course, anytime that there's potential problem with supply, people don't just sit around wringing their hands. The chemists and chemical engineers actually work together to develop new technologies. And some of these technologies are shown here. Propane dehydro is really not new. It's been around for probably a good 15 years. We'll talk a little bit about it. Olefin metathesis, one of my favorite chemistries. Olefin into conversion, sometimes called olefin cracking. Deep catalytic cracking, or DCC. And of course, methanol to olefins, or MTO. First, let's just spend one slide on propane dehydro. I say it's simple in concept, but difficult to carry out. I mean, it's very easy to draw this reaction. Propane going to propylene, give off hydrogen. But the chemists and even the engineers know this is not easy to do. It requires very high temperatures. It's a very endothermic reaction. At the same time, requires low pressures. And anytime you have very high temperatures combined with very low pressures and you have to pump in energy, it'll make it a fairly capital-intensive process. Nevertheless, there are, at last count, or at least by my last count, 9 propane dehydro plants in the world, making up 2.8% of global propylene capacity. So this is kind of like the biofuels part of the chemical industry. Small but growing, but important to supply incremental quantities. Okay, olefin metathesis. Again, this is really my favorite reaction in the whole world. It involves both a good reaction and propylene. Olefin metathesis was first discovered in 1964 by Phillips, Dr. Banks, who invented Phillips' ethylene polymerization technology over chromium catalyst, was trying to polymerize propylene, and he put propylene over this new catalyst he developed, and what he found coming out of the other end of the reactor was ethylene and butene. And he was sure that there must have been some mistake, and he told the technician that he hooked up the wrong tank. There's no way you can put propylene and get ethylene and butylene. But they double-checked, and sure enough, it was ethylene and butylene coming out, and they discovered a fundamental new reaction called metathesis, or olefin disproportionation. This is the first time anybody had ever seen this type of reactivity. If you look at textbooks before 1964, you will not find any mention of this type of reaction. It was totally new. The concept to use on a commercial scale was to take cheap refinery propylene at that time and convert it to higher value ethylene, and you get co-product butenes. They built a small plant to do this, but it was really never very successful. Lyondell was really the first to take advantage of this technology, but run it backwards. That is, to take ethylene, I think I have it this way, yes, if you take ethylene plus butene, it actually turns out to be a good way to make propylene. And of course, Lyondell at that time was supplying propylene to Arco, because Arco needed a lot of propylene to make propylene oxide. And that was really the first example of taking ethylene, combining it with low-cost butenes to make propylene. Now, some people might question the virtue of taking high-priced ethylene and downgrading it to propylene, but those people would have been wrong because they have had the last laugh, because now propylene is just as expensive, if not more expensive, than propylene. So it turns out to be a very good thing to do. And now Lummus has bought the rights to this technology and is now the leading licensor of metathesis technology around the world. IFP also has a competing technology. So let's take a look at what happens. This is a typical naphtha cracker. This is the output from a typical naphtha cracker. That is, if you feed 5.3 billion pounds, sorry, I'm from the US, I'm calibrated in pounds instead of tons, I apologize for that, but we get the same idea. So we feed in 5.3 billion pounds of naphtha, and we only get 1.6 billion pounds of ethylene. So you can see ethylene production from a naphtha cracker is not very selective. But nevertheless, we get a lot of co-products. We get 825 million pounds of propylene, we get C4s, we get C5s, we get lights, we get aromatics. So this is a typical feedstock slate. And we get what we see here is the PE ratio of 0.5. So if we put 825 over 1650, we get to 0.5, so that's the PE ratio as we talked about earlier. Now let's add a metathesis unit to it and see what happens. Remember I said we take ethylene, react it with butylenes to make propylene. So we lost almost 10% of our ethylene, but we increased propylene output by 54%. Pretty good. At the expense of low-value butylenes. So we lose 60% of our butylenes as well. So in this case, we have now increased the PE ratio from 0.5 to 0.85. And if you run this harder, that is, if you add more, this is an equilibrium reaction, and you can push the reaction. So if you use more of an ethylene excess, you can get the PE ratio above 1. And I believe this is the way the BASF Adofina is planning to run their metathesis unit. Again, the Lummus people can tell us more. Okay, so that's my quickie view of olefin metathesis. Let's now look at another technology called olefin interconversion technologies, or olefin cracking. That is that we catalytically crack our low-value C4 and C5 olefins that we get out of a steam cracker, a naphtha cracker. We can also get some C4 and C5 olefins from an FCC unit, put it over a zeolite type of catalyst, and out comes propylene in fairly high quantities. And we also get a little bit of ethylene, we get some lights, and we get some heavies. So unlike metathesis, we don't consume ethylene to make propylene, we actually make a little propylene, we make a little ethylene. Technologies for license, there are several sources available. ExxonMobil has one, originally called MOI, I believe they have a different name for it now. Kellogg is licensing what was originally a Lyondell process called Superflex. Lurgy has their version called Propylor. UOP has teamed up with Adofina to give their version. They have had many inquiries, but I don't believe none have been commercialized yet. And again, it's based on catalytic cracking with C4 and C5. This technology would be compatible with steam crackers and FCC units as well. Now, let's see what happens with with adding olefin into conversion unit. This is the same cracker I showed you earlier. Now let's see what happens if we add a superflex unit, for example, to it. Now what we get is that we increase ethylene production by 9%. We increase propylene production by 40%. At the expense of the C4 and C5 olefins, which have gone down. We've lost 88 and 90% respectively. Now let's look at the PE ratio. We've gone from 0.5 to 0.64. So that's kind of, at least the way I see it, maybe the licensors will feel differently. This is a trade-off between metathesis and olefin interconversion technology. We didn't have to lose ethylene to make the propylene. In fact, we gained a little, but we didn't increase the propylene nearly as much as we did with metathesis. So depending on what your end game is, that might decide which type of process is best for you. Okay, deep catalytic cracking is another technology which can be used and is used around the world to increase propylene. I don't know a lot about this. This is mostly a refining process of FCC unit. This is a typical output from an FCC unit. Say you get 4.8% propylene. And if you use DCC, which is really just a specially formulated type of catalyst and some tweaks to the unit, you can increase propylene up to 17%. But what you lost now is essentially your gasoline. So this is a trade-off. Do you want to make more propylene or do you want to make more gasoline? And if you're a refiner, you know, that question is changing maybe. Depends on the market at any particular time. Where can you make more money? So every day they would have to decide this, how they want to run their unit. And lastly, MTO. I know we're going to have some talks and we have a whole session. MTO, just briefly, we take methanol, put it over a specially formulated molecular sieve. In this case, the leading one seems to be SAPO34. And out comes the olefins, and out comes water, and out comes some side products. And when I say water, I don't just mean a little water. I mean a lot of water. This is shown here. Well, we'll talk about it in a minute. Two technologies for license really are the UOP process and the Lurgy process. No plants in commercial operation, but I believe some are in planning. In order for this to work, we think this will require very low-cost natural gas, but perhaps not as low as this since the competing technologies, the feedstocks for those technologies, are increasing. But it will require a world-scale megamethanol plant to support this unit, thus making this a very capital-intensive process. You're going to need to build a syngas unit, you're going to need to make a methanol synthesis unit, you're going to have to build your MTO unit, and you're still not done. If you're in a remote location, it's very difficult to ship ethylene and propylene, so you're going to need to make polyolefins as well. So if you add this all up, it's a very expensive, high capital investment on an unproven process. So all in all, fairly risky. So let's see what you get. This is a naphtha cracker. This is our old naphtha cracker, 32%, ethylene, 16%, propylene, no water. Of course, if you look at the MTO technologies, MTO and MTP, you get your olefins, the Lurgy process, they tune theirs to make only propylene. They actually make a little ethylene too, but they don't recover it. It's all combined in the lights. UOP process has flexibility to flip those ratios. I'm sure they'll tell you about it later in the conference. But look, we get 55, almost 56% water is an output. There's no way around that. Methanol inherently contains 56% water. And if you're making olefins, of course you're going to get 56% water. This is not necessarily a totally bad thing. If you're in a place like Egypt, you can use the water to actually get a byproduct credit for irrigation. So this is my last slide. This is my handy-dandy on-purpose propylene selector slide. So you can save a lot of money and you don't have to hire Chem Systems to help you. You can just use this chart. So this chart summarizes what the feedstocks are for the various things. Can you integrate this, or do you need to integrate this with a steam cracker? In these two cases, yes or no. They both work with either steam crackers or refineries. Propane dehydro standalone, deep catalytic cracking is a refining process. MTO, you don't need a steam cracker, although you could integrate it. Sensitive to ethylene price. What happens if the ethylene price goes up? How does that help or hurt your economics? In the case of olefin metathesis, it would hurt your economics because you use ethylene. In the case of olefin into conversion, it helps it. It's irrelevant to propane dehydro, and depending, it can help, could hurt here, and it would help your economics in MTO. Relative investment levels, moderate for these two technologies, fairly large for propane dehydro, moderate for deep catalytic cracking, at least as relative to other FCC processes, but very large for MTO. Commercially proven, there are several in operation for olefin metathesis. There are none yet, I believe, working for C4, C5 cracking. As I said, there are 9 propane dehydro plants. There's a handful of units, especially in Asia and China, using DCC, and no commercial units yet using MTO. So, this is, I think, a good summary chart. And again, the licensors will be telling you a lot more today and tomorrow about these processes. And I think I'm out of time, and I'd be happy to take any questions. Thank you.
Thank you, Dr. Plotkin. That was a very nice introduction into the olefins field. We'll talk more about that, as you said. Any questions? Yes, sir.
So what's your opinion about oxidative methods? I mean, oxidative cracking of butane, and what's the future of this method?
That's a good question, and it's one that's, of course, been worked on for many, many years. As far as, did you say butane oxidation?
Yeah.
Well, I think butane dehydro is not a particularly difficult process on its own, so I don't think the economics of doing it oxidatively will necessarily be that important in the future. I mean, it's interesting from a chemical point of view or a research point of view, but I don't see much future commercially for that type of process. Ethane, oxidative dehydrogenation, and propane, of course, are very interesting. And if somebody could develop a catalyst which would actually stand up over time, I think there could be very important developments in that area. And I know Dow has some very interesting patents in that area.
Yeah, but I mean oxidative cracking of oxidative cracking of fraction C4, C5.
Oh, okay, sorry.
For propylene and ethylene.
Yes, that I'm not aware of those technologies being that close to commercialization, but I could see that could be an interesting method, definitely.
Okay, let's stop.
I'll be looking forward to it.
Another question, please?
Just a question.
Just a second. You first, and then you.
A question concerning deep catalytic cracking. As far as I know,
I was afraid of that.
yeah. As far as I know, the gasoline produced with this process are characterized by very high contents of aromatics, and this is against the present regulation with respect to the quality of gasoline.
That could be a problem, and I'm sorry, as I said, I don't know a lot about FCC units to begin with, and not DCC. So if anybody's from Stone and Webster here, perhaps they can answer that. I really can't give a good answer.
We'll hear more about FCC later. tomorrow, I believe. Yes, sir?
My question is, just now you said that there is a plant is being
Please.
planned in China.
Louder, we don't hear you.
Could you tell me? Could you tell me the capacity and the technology resource and the plant name of the plant in China?
For DCC?
You said that there is a project being planned in China for MTO.
Oh,
Yes.
yeah.
Could you tell me the technology resource and the capacity and the plant?
No, I can't. The UOP guys are here, they could probably tell you.
But they use the Europe.
Yeah, one more question. Dr. Schultz.
Then another option, I think, for the propylene byproduct, the Fischer-Tropsch synthesis you didn't mention. As far as I understand, this Southern company, they produce some 8 million tons of product, and the selectivity is some 6%, and the present production may be 500,000 of tons of propylene, and most of this is being recovered now, and it could be different in the future in the iron catalyst and so on.
Yes.
You didn't,
You're right, I didn't mention that propylene is a byproduct for Fischer-Tropsch, yes.
It is, but it's already at present.
Yes.
Our colleagues from Southern can tell this easily, and it will be that iron be used just for the lower molecular weight product, not with the cobalt catalyst, but either of course, not in that option.
Okay.
Okay, well then, the ultimate question. Short response, please.
Absolutely.
Bertel Breeman, I'm from Sessel, and it's indeed true that in Schikuna we produce a lot of propylene by using iron-based high-temperature Fischer-Tropsch technology. So I can support the words of Professor Schultz. I'm an engineer, not a chemist. I have an economic question for you. What is your outlook for the propylene price relative to ethylene? Do you expect it will increase by this forecast? Can you speculate a little bit on that?
Yes.
That's the answer.
No. Nobody really knows for sure. I mean, you can engage us for a job and we can do a lot of fancy calculations on supply and demand, but I think the real answer is it depends. I mean, there's too many variables and too many uncertainties. If people really knew, they could make a lot of money. But,
Okay. Thank you very much, Dr. Plotkin. You're another